Good afternoon, everyone, and good morning to Michael Jordan, our author. So this is the Royal Statistical Society Journal webinar. My name is Richard Samworth. I work in the Statistical Laboratory at the University of Cambridge. It's my great pleasure to introduce Michael Jordan, who is the Sihong Chen Distinguished Professor in the Department of Electrical Engineering and Computer Science and the Department of Statistics at the University of California, Berkeley. He received his PhD in cognitive science in 1985 from the University of California in San Diego and has very wide research interests that span cognitive, computational, statistical, and biological sciences. Particular topics that he's worked on include, but are certainly not restricted to, Bayesian nonparametric analysis, probabilistic graphical models, spectral methods, kernel machines, and many different application areas. So it's my very great pleasure to invite Michael to give a presentation which will last something around about 20 or 25 minutes about a recent paper of his entitled A Scalable Bootstrap for Massive Data, which was published in the Journal of the Royal Statistical Society Series B in 2014. Michael.
Thank you, Richard. It's my pleasure to participate. So this is a talk about the bootstrap. In the era I started to work on this, a colleague had asked me, "What are you working on these days?" And I said, "The bootstrap." And he said, "You got to be kidding! No one works on the bootstrap anymore." And I hope maybe this talk and this paper will prod people to revisit the bootstrap. It's one of our great ideas in the field of statistics. It will be around forever in some form. And I think each generation's got to revisit it, rethink it. What's there? What are the new issues that arise in each era? So this is a paper about the computational side of the bootstrap. That's really not been a focus of most of the literature. There is a bit in the Efron and Tibshirani book about computation, but it's mainly focused on making sure the sampling procedure is relatively efficient computationally. So there's a bit of open terrain here. It's an area that one can contribute to. So we've done one paper, and there's this follow-up, which I'll allude to at the end of this talk. And that's about it. I return to other issues in my life. So there are quite a few remaining problems to be solved, and the questions, perhaps some of those will actually be about new research areas that one could engage in. I think there are really quite a number. So let me move to the first slide of my actual presentation. There's the title, and with the title, let me be very clear to acknowledge my collaborators here, Ariel, Kleiner, Purnamrita, Sarkar, and Ameet Talwalkar. We were a group at Berkeley working together. Ameet was a postdoc, and so was Purna, and Ariel was a grad student. And this work formed the bulk of Ariel's thesis. He's gone on to doing a startup, and Purna has moved to a faculty position at the University of Texas. Ameet is now faculty member at UCLA. This is quite a fun project, about a year or two of pondering and thinking and trying things out. Early on, we thought it was just going to be an application of something like the classical bootstrap or subsampling to class problems, and it turned out not to be that. So slide 2, we're just going to jump right in as statisticians, just get some notation. This talk will focus on a particular simple setting of IID data, the kind of classical bootstrap setting. So let's denote that data as x1 through xn. And from that, I'm going to have a functional on the data that I'll call a parameter estimate. It may not be a classical parameter. It may be a tail probability or a whole functional of some kind. And there's some procedure that we're going to not really specify, that a black box that takes the data and produces this parameter estimate. So our focus is inference, so we're interested in the quality of our estimate. It could be a confidence region, it could be a variance, it could be some other aspect of a risk function, something that's more inferential, and we're going to be interested in the computational side of getting that assessment. So let's call that Xi, and there will be a procedure that will run on the computer that will attempt to give an estimate of quality of Xi. So for concreteness, let's focus on confidence regions, but we could talk about other aspects of risk functions if we wished. Okay, so that's the notation on slide 3 now. Let's have a little bit of a diagram of what the bootstrap is. So this kind of sets up the bootstrap. If you're a frequent statistician, you run the thought experiment. What if I could collect more than the data I have at hand? I could collect multiple data sets, and I could keep doing this. So if you're the supreme mean, you can do this. This little diagram suggests this. On the left, there is the population from which the data are drawn. The supreme being possesses this population, so it can draw not just one data set, x1 through xn superscript 1, but also can draw multiple data sets, maybe m data sets. And from each of those data sets, you run the procedure to get the estimate. And we now have not just one value of the estimate, we have a collection. And of course, if you form the empirical distribution of those, you have an approximation of the sampling distribution. Then you put those values into a formula which calculates your, say, your confidence region or other assessment. So this diagram, of course, is just, I use this often in explaining bootstrap and statistical thinking to non-statisticians, computer scientists, because it looks like a kind of a little computing diagram. And in fact, there is something useful to take away from it, which is the bootstrap and this kind of frequentist approach is naively parallel. So if the supreme being has a cloud computer, it will be very natural for that supreme being in parallel to draw multiple times from the population and to compute the estimator in parallel multiple times and then bring them all back together to form the assessment. So in the computer science world, that's called the map-reduce paradigm. So you might imagine that the supreme being possesses a map-reduced computing platform to compute estimators and their quality. All right, so then we all know where kind of this goes next. We'll move on to slide 4. 5. And so this now is going to set up the bootstrap. We only have a single sample. We can't do what the supreme mean does and get multiple samples. So we take our single sample and we form, at least conceptually, the empirical distribution of the sample. So here it is in the form of a histogram. And if we move on to the next slide, we recall that there is a theorem, an empirical process theory that says that this empirical distribution is an approximation to the true population. It's a uniformly good approximation, both uniformly on this x-axis here and uniformly in the space of probability distribution. So that's Glavinko-Cantelli theorem. So with that as support, theoretical support, on slide 7, you erase the population, which you don't possess, and you take the object you do possess, this empirical distribution, and you note that it is a distribution. It lives in the space of distributions just like the population does. And it's close to the population, so you pretend that it is the population. For you, it is the population. And now on the next slide, you return to your flow diagram, and where there was the population before, you plug in the empirical distribution. And the rest of the diagram is exactly the same, only that we've put stars on all the quantities to denote that this is the bootstrap version of the diagram and not the supreme being's idealized version of the diagram. So that's Efron's brilliant idea. It is just a plug-in idea. We plug in for the population an empirical entity and go from there throughout the rest of the diagram. The theory of the bootstrap, there are many attempts to put level of theory on this, and the kind of the first starting place is simply functional analysis, where if you note that if you're in a situation where all the operators in this diagram are continuous in a functional analytic sense, and I'm putting in an object which is close to the supremum norm to the truth, then that continuity will flow through the diagram, and psi, the output, will be close to the quantity, the true quantity, the quantity the supreme being computes. So that is a proof, and so if you have a Hadamard differentiability or some other form of functional analytic differentiability of these operators, you are good to go. You have a consistency proof and even a rate. And then Peter Hall also wrote extensively about theory of the bootstrap using Edgeworth expansion and trying to recover the notion that trying to establish a rate for the bootstrap, and in fact it showed the bootstrap has a very appealing rate. It is second order correct, or it can be made second order correct, such that this diagram doesn't suggest that, but it has preferable properties to asymptotic expansions. Okay, so that's all just reminding us where we are, where the literature is taking us to. And now I want to think about the computational issues. This project was generated in the era we were working with colleagues who had large or massive in the title of the paper data sets, so terabytes. So imagine that empirical distribution on the left is formed from a terabyte of data, which is nowadays not uncommon. And if you sample a terabyte of data with replacement, which is what the bootstrap is effectively doing, you will get data sets of size 632 gigabytes roughly. And so if you think about this diagram as a parallel computer that's resampling the empirical on the left repeatedly, it's these 632 gigabytes down each one of those arrows on the left. And you simply can't do that on any kind of a plausible modern computing system in any realistic amount of time. So even if your basic estimator is very quick to compute, it'll take you tens of minutes at least, but probably more like hours to actually run a bootstrap on something of this size. So that just makes it infeasible for computation in the kind of industrial setting that we had in mind. We talked to our partners about this, and they said, well, that's just not viable for us. We have to return. They were doing IT sorts of things. We have to return an estimate, and if you want to give us error bars, that would be great, but they need to be computed roughly in the same amount of time it takes to calculate the estimate. So in milliseconds time scale. So this is a puzzle. How in the world are we going to use our wonderful tool, the bootstrap, as data sets get larger and larger, even if parallelism doesn't save us, because each replicate is too large to put out on a network to make the thing compute quickly. Here is a slide 9, that just summarizes just exactly what I just said. So large data sets lead to large resampling, and they would flood the network, and it would all take way too long. Okay, so let's move on to trying to solve this problem. So page 10 is kind of the next thing you might think about. So subsampling is another paradigm that takes the empirical distribution, or it takes the original data set of size n. And on page 11, we show that we form a subsample of size b. And you should roughly think of size square root of n to get the fixed ideas. So a much reduced subsample. And this is just a natural idea. In fact, we were not gurus in this area and had to pick up the Politis et al. Book to learn about subsampling. It's an extensive literature of its own, a very beautiful idea, many, many applications. And so we learned about it, and we certainly felt this was probably the viable paradigm. You have to do some kind of divide and conquer with big data sets and break the thing up into pieces to put things back together. And this is where it got conceptually interesting, because in statistics, breaking things up into pieces is problematic. In statistics, we want to bring things together, aggregate. That's how we get power. That's how we get concentration. So when you break things up into pieces, you somehow lose statistical power, and you have to correct for that somehow. And in particular, if you naively simply take our data sets of size B, and of course we can form n choose B of them. We can subsample from the data set of size n, data sets of size B in n choose B ways. We have a huge number of them. If we simply take them as data and run an estimator and form an empirical sampling distribution of that, of course it'll be too wide. The estimator thinks it has very little amounts of data, so it'll form confidence region, which is accordingly much wider. And so a naive approach to divide and conquer here just completely fails. You have, if the error bars are going as 1 over square root of n, you're off by a square root factor. So if I subsampled at ratio 10, I took every 10th data point, then my error bars will be off by a factor of square root of 10, a huge number and completely infeasible. So, of course, the people working on subsampling are aware of this, and so on page 12, we suggest that the issue that they faced, which is that we're on the wrong scale, so we have to analytically correct the error bars. So what they did is, in fact, take the data set to size B, and they formed some sort of an assessment, confidence region for that, but they rescaled the error bars to make them smaller. So if we believe we have an estimator who has error bars at scale square root of the size of the sample, we would multiply that by square root of b over n and correct. But this is problematic. You don't always know what the correction factor should be. You would have to estimate that in general for data. But nonetheless, it felt like the right path to pursue, and so we started to pursue it in the context of our large-scale problems that we had and I should add that we actually had a parallel computer. At this time, Amazon EC2 had come online, and so it was easy to get hundreds to thousands of computers running for you simultaneously on your problem. And in fact, when I had become aware of this kind of paradigm, this cloud computing paradigm, it just seemed clear to me as statisticians this was a wonderful moment because we suddenly had the possibility to resample in parallel at large scale. We should be just using that immediately for inferential problems. So we tried it out, and here just is a reminder of kind of what subsampling does on page 13. Let's move on to page 14. This is a particular example of an experiment we did kind of early on. This was a multivariate linear regression. We had a covariate vector of size 100, and we had 50,000 data points in synthetic data. This was just synthetic, so we had a student t distribution generating the x coordinates, and then we just had a Gaussian model, and we estimated a parameter with least squares. Then we calculated marginal confidence intervals for each of the components of this parameter vector W, and we took the relative mean absolute deviation from a true confidence interval, and that was gotten by a long Monte Carlo run to find the truth. Then we subsampled various sizes. We took n to the gamma for various sizes of gamma running from 1/2 up to 1. And so square root of n up to full data set in which you would get no advantages. And so we did this with a whole range of experiments. And here is an example on page 15 of the kind of results that we found. On the x-axis, we have time, and that's really important for us. This isn't the number of subsamples. This is time, because that's what we really care about. We'll all talk on how long does it take to get a reasonable confidence interval. That's what our industrial partners cared about. So we have time on the x-axis, and we have this relative error on the y-axis. And so the bootstrap is the blue curve there. It kind of comes down relatively quickly and stabilizes. And then subsampling for various exponents are plotted as well. So for the exponent 0.5, so square root subsampling, that's the black dashed line at the top. And so it's just failing at this, at least on this time scale and at this aggressive subsampling rate. So if we brought it down to 0.6, that's the green curve, and now it's starting to get better. Interestingly, at 0.7 and 0.8, it actually is beating the bootstrap in terms of computational efficiency. It's giving an answer more quickly than the bootstrap, and the answer is of higher quality, at least early on. But then, problematically, if we go back up to 0.9, it's poorer than the bootstrap and quite inaccurate. So this is interesting in two ways. First of all, there's a bit of sensitivity here. And secondly, it actually, there's a possibility of beating the bootstrap in a computational sense. It's maybe not the optimal way to subsample or to resample, to take all of your data in one big blast to resample. So we kind of noticed that and we thought that was interesting. We then read more and learned that there was quite a literature on evaluating subsampling, and that literature continues to this day. So in fact, our host, Richard Samworth, who had written a very interesting article on subsampling, had noted its instability to this parameter of kind of the subsampling size, doing some theoretical analysis and perhaps empirical as well. And so what we had done here is just to kind of rediscover what Richard had noted, Richard and others, about there is an issue with subsampling. So if you knew what the right subsampling rate was, and you might be able to figure that out in some cases, that it would be the right thing to do. But if you don't know what it is, you have a worry that you're picking the wrong value and you're getting actually inaccurate error bars, and you wouldn't know that a priori, you wouldn't know it a posteriori necessarily. So we thought we were a bit stuck here, and we kind of went back and to the whiteboard and thought about it a bit more. So let's move on, page 16. So eventually a new idea came out. At least we still to this day think it's new, even though it's extremely simple. So that was kind of surprising that as big as this literature was, that something new could be done. And it really combines the idea of the bootstrap and subsampling. It's not wildly novel in some sense. In some sense, it really is the bootstrap, but using subsampling spirit. And in some sense, this slide argues it gets the best of both worlds. It's going to work with small subsets of data, just like subsampling. I think that's critical. You can't expect to move forward in this modern world with subsampling at scale 600 gigabytes. And it's going to work with distributed and parallel computing platforms just very naturally. It doesn't require analytical rescaling. So it's like the bootstrap in that sense. It just runs. So let's talk about what it is. Next slide is page 19. So it's really simple. It takes the subsampling paradigm a little further. So let's return to that diagram. We have the population, which generated a data set of size n. From that, we are going to subsample a data set of size b, okay, just like in subsampling. Then we will not simply apply the estimator to the subsample of size b. What we're going to do at this stage is bootstrap the subsample. So let me argue why that's a reasonable thing to do. So on page 20, let's note that the subsample itself is coming from the population. There was an intermediate stage in which it went through the main sample, but that is now been subsampled with an independent, with random sampling. So this subsample is coming directly from the population. Forget that there was an intermediate stage. All right. So for the same Blavinko-Cantelli reasons, the subsample empirical distribution is an approximation of the underlying population. It's a uniformly good approximation. As suggested by my slide, in which there's something like 10 data points, it's not as good an approximation as the full data set, of course, but it nonetheless is mathematically an approximation to the underlying population, uniformly good. So if we're to return to the original diagram and plug in the subsample as our population, we could then resample the subsample and do exactly what the supreme mean is doing, using the subsample as our estimate of the population. And here's the key idea. Extremely simple, but the key idea is that while the subsample is based on B data points, its support is a discrete distribution on B points, you can resample as many times as you want. You can resample it once and draw from those B points. You can do it twice. You could do it B times if you were to choose to do that, but that would be wrong. That would put you on the wrong scale. You can resample this object N times, right? And so if you were dumb, that would create a new data set, a resampled data set that was of size N, and that's what we argue we don't want to do. But you wouldn't be dumb at this point. You would note that you have B points, and you would just keep a count of the number of times each one of them has been resampled in the bootstrap resampling. So we're creating data sets of size N, but their size in a computing sense is of size B with a counter attached to each of the data points. Okay, so that's the key idea. We bootstrap a subsample. Right? So here on this next slide, which is slide 24, I'm just saying what I just said. So we're taking an object of a certain size, but it is nonetheless a distribution of space of distributions. It can be sampled as many times as you want. So let's indeed resample it with replacement N times, not B times. Okay, so that gets rid of the need for analytical rescaling. You are sampling on the correct scale of your uncertainty, which is the size of your original data set. Okay, so now we have this diagram, which really is the main part of the talk. This is page 25. So this summarizes everything. Hopefully it's now entirely clear. We take our original data set of size maybe a terabyte on the left, and the first thing we do is we form a subsample from that. And so in the experiment I'll talk about in a minute, that subsample is of size 4 gigabytes. So that's kind of a square root of n size subsample. So a 4 gigabyte subsample goes along the first arrow on the upper left there. 4 gigabytes is small enough that it can go blazingly fast on modern computers. So it arrives in the box at the top, where in parallel there's a bunch of processors or threads on processors that are going to run the bootstrap on that subsample, as if that was the original data that you had. And so that upper box is just the bootstrap, and it's working on scale of sort of 4 gigabytes. So the operations can all be fast. Again, you keep weighted data sets with counts, and you never form data sets of size n. That would then slow you down. So that upper box just runs the bootstrap, and it outputs an answer, which is, in Peter Hall's sense, a correct bootstrap. It is just going to be noisier because it's based on a subsample, which is possibly unrepresentative. It'll have extra bias and extra variance. So instead of using just one subsample, of course, you do, as in subsample, you use multiple subsamples. So the remaining boxes on the slide are just simply doing the bootstrap now on multiple subsamples. Each one of them is outputting a conceptually correct bootstrap. And so you take all those multiple bootstraps and combine them in some way. So in our original paper, we just simply suggested taking the upper, say, quantile, averaging the upper quantile, and averaging the lower quantile, and returning that. That's not a particularly appealing, mathematically appealing way to do it. One might want to think of that object as a distribution and find a collection of distributions and find a single distribution which summarizes that, perhaps with earth mover distance or Wasserstein or some more pretty way of doing it. But nonetheless, one aggregates the results of multiple sampling distributions. And there's many ways to think about doing that. But in fact, research could be done here on that. So hopefully that is clear to everyone. So let me now then move on and so I'm going to get hopefully pretty quickly to an experiment here and try to close up relatively quickly. So this again summarizes some of the things I've just said, that if we're working with a terabyte of data, this whole procedure will never require more than about 4 gigabytes to be going down on the network in a computer. So we'll move on to slide 27. This is returning to that experiment we did earlier with the regression. And we again see the bootstrap curve coming down, and now we see this new procedure, BLB, for multiple values of the exponent from 0.5 to 0.9, doing well, giving a result of as high quality as the bootstrap. And again, interestingly, seeming to be more quick to get that answer, quicker than the bootstrap. All right, so that led us to really try to do some real experiments at scale with original data sets, and I'm going to show you one that was in the original paper. So on page 28 is our kind of killer app for this. So this is a logistic regression done on about a quarter terabyte a day for this particular experiment. We did sort of hundreds of experiments. This is just one of them. We're just doing a logistic regression. We're trying to simply get marginal confidence intervals on each of the coefficients of a large-scale logistic regression. So again, we ran a very long, many days Monte Carlo experiment to get kind of gold standard confidence intervals, and we're comparing to that. So relative error on the y-axis is comparing to those Monte Carlos. And now we're going to try to compare our new procedure, this BLB procedure, to the bootstrap. And as I've argued, the bootstrap just can't be done on this scale. It's going to generate data sets which are too large, and it'll take forever to do that. So what we did here is we took the bootstrap, we took the logistic regression, and we parallelized logistic regression so that each run of a logistic regression was as fast as possible. So we're doing this on the Amazon EC2 platform, and we simply use kind of modern parallel gradient procedures where you compute in parallel gradients for all of a data set in pieces, and you reaggregate those to compute an overall update. And so you can make each iterate as quick as possible using IRLS, iterative related least squares. So that's what we've done with the bootstrap. It's actually a sequential procedure using a parallel computer for each iteration. So on a central computer, we took the entire large data set, a quarter terabyte. We resampled with replacement. We sent that large, 200 gigabyte resampling up to the parallel computer. It ran logistic regression very quickly in parallel. And then we did that whole procedure again. We resampled on the central computer, got a new resampled bootstrap data set, and sent it up to the parallel computer and so on. So those are the blue dots coming down. You can sort of see how long one logistic regression run takes here. It's the distance on the x-axis between the blue dots, so on order of 2,000 or 3,000 seconds. So that comes down and starts to asymptote at about 15,000 seconds, and you're getting a relative error of about 0.25 or something like that. If you keep going for many more tens of thousands of seconds, it will go down further, and of course it won't go all the way to zero because the size of the data is being held fixed. That took quite a bit of time for Ariel Kleiner to implement. It required a bit of engineering to be able to set up this parallel logistic regression and so on. On the other hand, the BLB procedure took not very long at all. It was done on the Spark platform at Berkeley, and it was just that parallel diagram I showed you, just implemented on a parallel computer. So it took very little time to implement, and the results are the red dots. So this thing is just that parallel diagram run once. You just flow the data through. In parallel, you do these bootstraps, and you reaggregate. So the overall time for that procedure was about 200 to 300 seconds. And the error was about half the error of the bootstrap even after 15,000 seconds. So I find this a very striking diagram. This is order of magnitude improvement in a real-world measure, time, to get an inferential quantity. So our colleagues at places like Google and have used this procedure. It fits. This is just academic kind of building it to get it down to 200 seconds. But if you're an engineering team at a big company, you can, from 200 seconds, you can get it down to potentially whatever you want it to be with specialized software and hardware. So just by reorganizing the bootstrap computation, not just doing a naive resampling, you can do the bootstrap, in a way that scales with modern data sets. So I found this striking. I should say, even in public, I think it's okay to say something good about JRSS. We sent this to another journal. I started to say which one, but let's not say. And we were rejected very quickly. The reviewer said, no one's interested in the bootstrap anymore, and this looks like it's just computer science work. It's not of interest to statisticians. And I was, of course, pretty disappointed. I looked at this picture here and I said, this is important. This is something that will matter for us statisticians to play a role in modern large-scale data set. If we don't, other people will do it, and we should be teaching them how to use ideas like the bootstrap. So we just put our tail between our legs and sent it off to JRSS, and it was accepted with very interesting reviews and a very nice reception. And so that was a pleasure. I'm going to end now. Let me just say I do have other slides here that people can choose to look at. First of all, I'm going to skip over some theory. We just read the Peter Hall book and applied that theory, not entirely correctly, by the way. There is a little bit of a glitch that we were able to fix later, but nonetheless, we were able to do this. And this was what the original journal asked us to do, is put in some theory. I don't think this theory is at all interesting. The interesting thing is the slide I just showed you, but that's what you need to do to sometimes get published, is to have a bit of big O notation. And this other slides, which I will skip, but just to let you know what is here, is we did have one follow-up project actually building these kind of ideas into a real-world database system called BlinkDB. It's a database system that you put in a query and get an answer always with an error bar, which is not common in the computer science literature at all. So we put it in there and really started trying this on real-world data sets that were very large and had heavy tails and all kinds of interesting statistics, not the mean, not the median, all kinds of user-defined functions, and did some real benchmarking to see how good the error bars were using Monte Carlo runs. And comparisons were made to asymptotic expansions, to large deviation bounds, and to bootstrap. And you can look at these slides, you'll sort of see it's daunting. It's uncomfortable that in sort of 90% of the cases, bootstrap error bars were good, but 10% they were just poor. And it was worse for the asymptotic expansions and for the large deviation bounds. So we took this problem seriously and started developing diagnostics for calculating confidence intervals, diagnostics for the bootstrap. And I don't know if there's a literature on this. I'd be curious if anyone could tell me if there is. But it really turned out to be important to work out some diagnostics. We did, and we were able to compute them very quickly so that you could run these procedures and have diagnostics tell you that these error bars that we're producing are actually likely to be good, and then provide them back to the user. If the diagnostic said the error bars were not likely to be good, we would tell the user that, and we would run a very slow Monte Carlo run and give them good error bars, but much, much more slowly. So that project called BlinkDB, there's papers on that, and you're welcome to see. There's a whole long list of authors there, including us statisticians with some real computer scientists. So I'm going to stop there. That's what I wanted to say. Again, just to summarize, I think bootstrap and subsampling ideas are really critical for statistics. Mostly, if I give these talks in statistics audiences, they say, "Yeah, but that's all true, but bootstrap has got many, many problems. No one should be telling anyone to use the bootstrap." And I'm aware of those problems and issues, but I think that we should be telling people to use the bootstrap because they're not using anything out there. So at least get them on board with the idea of the bootstrap is. So thank you very much.
I wonder, Michael, if you can just say a little bit about how this whole project arose. I mean, it's a new topic for you. As you said, it was your first venture into the bootstrap. Was it one particular application that you had in mind where you felt that people would want to use bootstrap methods, but it was computationally infeasible, or was it just that you could envisage many possible scenarios where that might be the case?
Thanks. Yeah, Richard. I kind of alluded to this issue along the way, but let me now kind of pull it together in a little package. This was done in the context of what was called the AMP lab at Berkeley, which was a group of computer scientists mostly, and me as a statistician, trying to work on data analysis platforms. And so I really thought it was interesting to pair with them and sort of change computer science to make it more inferential. So we were working with this AMP lab. It still has a website you can have a look at. There was 30 companies at the end that supported us, including Google, Facebook, Microsoft, Amazon, and so on and so forth. And so we were working with those companies and writing software that in some sense competed with theirs and eventually actually prevailed. So the main project that got market share out of the AMP lab was called Spark, and it is to this day probably the most widely used large-scale data analysis platform in existence. So I was not involved in the actual work there, but I helped motivate it, and my students, by complaining about Hadoop not being good for statistics, that led to Spark being developed, because it's a caching version of Hadoop that allows you to do iterative kind of procedures like we do in statistics. In the early days, as we were kind of thinking about things to work on, I kept saying, well, look, folks, we always have to have confidence intervals and considerations of bias and sampling ideas throughout our infrastructure. Let's not just build a data analysis system that doesn't do that. That was being taken seriously. I tend to be a bit more of a Bayesian in my just kind of pure statistical work, because I often will work with a scientist, say a biologist or a physicist or something, for a year or two on a data set, kind of the classical statistical setting. And in that setting, I want to extract a lot of knowledge out of my colleague, my biologist friend or physicist friend. And I find it very natural to put that knowledge into a likelihood, but also even eventually into a prior, and work on a particular data set, so I condition on the data set. So I find it comfortable to be Bayesian in many of my applied projects. But here I'm in a very different world. I'm trying to work with a team developing software that will be used by people, indeed has been used throughout the world, hundreds of thousands of millions of times. So I need a frequentist guarantee, almost by definition, for the inferential quantities that we give out. This is not the realm in which to be a Bayesian. This is the realm to be a frequentist. And I believe that for software development. So I just said, okay, I'm going to be a frequentist. Let's go in and look at the kind of setup. And immediately it was clear we worked with Amazon EC2. We had hundreds of computers, and my colleagues had no idea what to do with them other than make the basic algorithm faster, kind of in a machine learning style. And I said, no, this is a big opportunity. We can now start to get inferential quantities. We can resample. We can do all that. And so I was aware of the bootstrap, and I quickly, pulled Efron Tibshani back off my bookshelf. And I said, this is a natural match. Cloud computing, bootstrap. We should make this match real and see what problems and issues arise. So we formed this little team and started to both work on the software side, but also to do the work that I've reported on in this paper. Something interesting came out of it. And, I think there's many other things to do. You can now return to all the other bootstrap techniques like, the wild bootstrap or the block bootstrap, or, think about time series, think about what if your data were already split up in a certain way because of the way it was collected, and how do you take that into account? And how do you do this with cross-validation and not with bootstrap, and so on and so forth. So I try to motivate some of the successive generations of students to work on things like that, but they've mainly gotten focused on theory and concentration bounds and networks and all kinds of other problems. That's kind of where we've been. But it's just a natural match of the bootstrap and frequentist thinking with kind of one aspect of modern computing and architecture. And that's why I started working on bootstrap. But with some tentativeness, because whenever you get into a new area that you're not a guru in, it's a little frightening.
Yeah, there's a lot of startup costs. Okay. And in terms of sort of other groups that you've seen that have picked up this general method, have they tended to be from industry, from science, and do you know any applications where it's been specifically applied by others?
It's been used in industry quite a bit. Various of the companies I named earlier have been using it for problems. They really have to be kind of coaxed into even the concept of having error bars. In fact, often their error bars aren't what I would call truly inferential. They're based on taking a very large data set and just subsampling the data set in the first phase and running queries on the smaller data set so they could be faster. That's a whole area of database where people do that. And they're aware that when they do that, they are getting errors incurred by their own sampling, and they should put error bars on those. But they don't tend to think about there was an outside population that generated data, and I want error bars with respect to the outside population. Nonetheless, it's kind of a work in progress to get people to be interested in this, and they have been using it in various companies. I'm also aware of some science applications. Some high-energy physicists have been using it. And I just hear, here and there for, people asking about it. And often they will write to me and they will say, well, we need to extend it in this or that way. And I'll say, well, just go back to the original Bootstrap and just do that. There was all this literature. So I hope my role here is just simply to kind of get people to rethink and to feel energized that they can do new things with it.
If I could just talk a little bit about the algorithm itself, it seems to me that there are, you have a few choices to make, some tuning parameters to the algorithm. In terms of, so S is the number of things that you're averaging over. So it seems clear to me that the larger S is, the better you expect to do statistically, but the longer it's going to take you to get there. What's not quite so clear to me is the choice of B here. I think probably that would also improve performance statistically as it increases, but I guess there may be some of these sort of non-standard settings where actually there is some sort of trade-off there. Do you have any thoughts on that?
Yeah, good question. There are three parameters here, which is two of them are relatively easy to set. One of them is the number of subsamples you take, and that's done totally in parallel. And you're absolutely right there that parameter, the more the better from a statistical point of view. And it actually doesn't slow you down if you're working on a parallel computer. It's really completely naive parallelism. So that's perfectly fine. And we have kind of it's the usual sort of do it a few hundred or a few thousands of times if you can afford it kind of thing. There's also then the number of iterates inside of a bootstrap, and that's again a kind of a classical thing to set. Number of resamplings within a single subsample for us. And again, that's back to kind of the usual argument in literature. Efron, Tichrani suggesting maybe hundreds for estimation, maybe thousands for testing, and later people suggesting, well, we got more resources, let's do tens of thousands. So those are relatively straightforward. And the third parameter is indeed the subsample size, which we call D here. Our theory, which is an asymptotic theory, shows that the procedure is provably correct if D is bigger than square root of n. Below square root of n, it may work, but the theory does not support that. And above square root of n, it's guaranteed to work, but only asymptotically. And so we found that when D was chosen to be n to the 0.6, in a lot of our Monte Carlo experiments, it would work, but then occasionally not work. And so our default suggestion for people has been n to the 0.7, which slows things down a bit, but is not failed mostly for us in real experiments. But that parameter we don't have theory for. It's the same kind of parameter there's not really theory for in the M out of N bootstrap and in subsampling. In both those paradigms, setting M is still really kind of an open problem. There are, Peter Bickel worked on a particular kind of way of doing multiple values of M and extrapolating or interpolating to find a value of M.
Sure.
But that parameter we don't have a theory for, and that's a good open question. I do think I personally want to return to it. I think it's actually solvable, and have a bit of ideas on how to do that. Let me just kind of add on there that there was a glitch in our theory in our appendix, and it really was that the Peter Hall analysis was for a classical fixed number of parameter setting. And our setting here actually requires a high-dimensional analysis where the number of parameters and the amount of data are both getting large together. And so you need a new version of Edgeworth expansion, which is a high-dimensional Edgeworth. So there's a student at Berkeley, Li-Hua He, who has worked on that and has come up with a kind of a more satisfying high-dimensional Edgeworth analysis approach that does apply to this setting and kind of poses that issue. And it may be of independent interest of its own.
Sure. So I guess maybe it seems to me that the theory is mainly concerned with the kind of regular root n rate of convergence type of setting, if I've understood correctly, but maybe I haven't. And so there it seems that that increasing B should help you statistically.
That's right. It is. We did, the only theory we've done is the regular root n array. That is again open to kind of try to get trade-offs, and I do agree with you. There are trade-offs to be had here in the non-standard situations. I should say, setting B is very different from in subsampling. If you set B in subsampling to be very large, in fact, take the limiting case where B is the entire data set, B is equal to n. Then you only have one subsample, and you get one value there, so you don't get a sampling distribution at all. You get simply a single point. So it fails at that limit, and as you get close to n, it will also fail. There's not enough entropy to get a good estimate. So if you pull back, you start to get into a range where it worked, as you're aware in your work, and then we showed empirically here. But this new procedure, back of the bootstrap, as you go towards n, it simply reduces to the classical bootstrap. And so when B is equal to n, you are running the classical bootstrap, and it works. It's just slow. So in that sense, we're less sensitive. It's less of a trade-off for that basic parameter than in subsampling.
Sure.
But you're absolutely right. I think there's more sophisticated or subtleties will come up in non-standard situations where the statistical quality will depend on B. It won't just be monotonically better. And indeed, I think there's subtleties in it. What you're doing is you're breaking apart the statistical problem into smaller problems. And it's not just that they're faster, they're, there's an entropy energy kind of trade-off. And so you will incur a little bit more bias and variance by working on the smaller, bootstraps. But then when you aggregate it the right way, you could kill off some of that variance, certainly, but even the bias. And it may be that there's interesting subtle trade-offs on how you re-aggregate. So many open issues there as well.
Yeah, okay. I could say more about that, but maybe let me move on to another sort of general topic. This is an issue that Alistair Young brought up. He said he was saying there was a lot of work in the 1990s on various computational tricks for the bootstrap, and he also asked a question about whether it might be worth actually avoiding Monte Carlo completely. Having done this sort of breaking up this problem into lots and lots of subproblems on the subsets of size B, could you use analytical approximations? I think he had in mind things like saddle point approximations here on each of the subsamples.
Excellent idea. I don't necessarily have the intuition that so you break them up into smaller things. Certainly the asymptotics is now worse for you. And so, if you do higher order expansions, higher order saddle point sorts of things, maybe you can get by with them, more cheaply. But no, I don't have it's an interesting thing to think about. I've worked on variational approximations in my life a lot, and those are actually, in some sense, a form of saddle point approximation. And I'm always kind of attuned to the idea that you can do things more cheaply if you take higher order expansions. And then when you put them back together, there's opportunities for doing that in a smart way. So that feels like a pregnant idea worthy of thought. And I don't maybe have exactly the right intuition about why that would be appropriate. But, it's not the asymptotics that you're getting there. It's presumably there's something else about the smaller size which is working in your favor. But if you want to jump in there and say more about that, it sounds interesting to me.
Well, I guess that's something that's particularly that Alistair has been interested in for a while. Thank you very much indeed for taking the time to give us this fascinating presentation on what I think will turn out to be a very influential method.